So today, as part of statics, we're going to talk about the dot product. This is used quite extensively in statics, so it is a pretty fundamental topic to know, but fortunately it is not very difficult. So a quick definition, the dot product is the product of the two magnitudes of two vectors and the cosine of the angle formed between them. So that means that a dot b is equal to the magnitude of a multiplied by the magnitude of b times the cosine of the angle between them. So simply put, this is just the similar components of each vector are multiplied together then added. So for example, the x component of a times the x component of b plus the y component of a times the y component of b plus the z component of a times the z component of b would equal a dot b. So some laws of dot product, commutative, this works. So a dot b is the same as b dot a. The associative law also works. So any scalar times the dot product of a and b is equal to a dot, say the scalar is m, so a dot mb, which is equal to ma dot b. Basically, the scalar can be anywhere. It doesn't really matter how it's multiplied in. And then the distributive property also works. So a dot b plus c is equal to a dot b plus a dot c. In terms of orthogonality, vectors are orthogonal if their dot product equals 0, just based off of cosine of 90 equals 0. And they'd be parallel if the dot product equals 1, because the cosine of 0 degrees, which is the angle between parallel lines, is 1. So the magnitude of a vector is the square root of a vector dot product itself. So for example, a dot a would be equal to the magnitude of a times the magnitude of a times cosine of 0, and this is just equal to the magnitude of a squared. The angle between two vectors is the inverse cosine of the dot product of the vectors divided by the magnitudes. So this is just rearranging that fundamental formula. A dot b equals magnitude a times magnitude b cos theta, and if we rearrange and solve for theta, that would leave us with arc cos a dot b over magnitude a times magnitude b. Projection is a very useful application of the dot product. So we can project a vector onto another, so we can see which components of the vector lie on another vector. To do this, we just dot the first vector and the unit vector of the second. So an application in statics is if you want to project a force onto a direction vector. So say, for example, you have a force acting on a line, then you'd find the position vector of that line and find the force vector. Sometimes these are already given, which just makes it easier. And then find the unit vector of the position vector, conduct dot product operation on the force and unit vector, and then convert the result into CVN by multiplying the force by the unit vector. So fairly simple. There's an example of that. So in the video, we'll just go over a dot product example and an example of finding the angle between two vectors using the dot product. And in the extra example, we do a projection. So you can see that in the link below, as always. So we'll go into this example here. So we want to dot. So we'll just do the dot product. Example first. So go u dot v. And these are both vectors. And u is 1, 2, 4. And v is 3, 6, 2. So then all we have to do is multiply the components. And then add them. So we'll do that now. So 1 times 3 is, well, I'll write it out. 1 times 3 plus 2 times 6 plus 4 times 2. This is equal to 3 plus 12 plus 8. And this is simply equal to 23, if my calculations are correct. So that's pretty simple. So you can see the dot product is pretty simple. And an important thing to remember is that you'll end up with just a scalar number. It's not going to be another vector. It'll be a scalar. Just to show you what this might look like. Now, this won't be exact because it's drawn in 2D instead of 3D. But if you have a vector, say v1, you want to project it onto this vector v2, the resultant vector would be this, this vector here. So basically you can see that that is the component of v1, which is on v2. Next, we'll go over how to find the angle. Between the vectors. So I believe we're using the same vectors. Yes, we are. So we know that just rearranging the formula. So let's see, u dot v is equal to u v cos theta. So we want to solve for that theta. Which we can do u dot v over magnitude of u times magnitude of, v is equal to cosine theta. And then if we take the inverse cosine on both sides, we'll end up with cos negative 1 or arc cos u dot v over magnitude u times magnitude v equals theta. And then we can just fill it in here. So I'm going to do it sort of all in one big step, but I'll show all the steps. So I'll say cos negative 1, sorry, this should have brackets around it, cos negative 1, and then u is 1, 2, 4. Well, we already found the dot product, so I'm just going to go ahead and use it from up here. So we have 23 over square root 1 squared plus 2 squared plus 4 squared multiplied by the square root of 3 squared plus 6 squared plus 2 squared. And this will give us arc cos 23 over, well, I guess we can say, so 1 plus 4 plus 16 is 21 times root 9 plus 36. Oh, that should be a plus. Sorry, 9 plus 36 plus 144 is 189. And just putting that in the calculator, you could simplify, I suppose, or do more by hand, but at this point it would just be just as easy to put in the calculator. So that would be equal to, let's see, so that's 23 over root 21 times root 189. So that's, oh, sorry, didn't have to write all that out. So then we just get theta is equal to 68.6 degrees. And that is it. All right, thank you for watching. I hope this helped. Thank you to Loom and Google Keep, and to my professors as well. And we'll see you next week.